Okay, so for this part, we talk about the potential, electric potential generated by the electric dipole. Yeah, so actually it is similar to what we try to find the electric field by an electric dipole, and even more simple because this electric potential is a scalar. So we just add them together, which is easy. So in this case, we can actually find the potential at arbitrary point in the space rather than on the z-axis. If you still remember, for the E field, when we try to find the E field generated by the dipole, we actually find the E field on this z-axis. But here, as this one is easier to calculate, so we can actually find arbitrary point in the space. So in this case, we also have a d equals to the distance between the two charges, and r is from the center point of the dipole to point P, and yeah, r plus and r minus are the distance from the positive negative charge to point P. Okay, so so the total potential generated by this dipole is nothing but V plus generated by the positive charge and the V minus generated by the negative charge. And yeah, so for V plus, it is nothing but K times Q over R plus. And then for V minus, K times negative Q over R minus. So nothing special here. And then we can just take the common denominator for these two fractions and then just subtract them like this. And then actually this Q can be factored out, so we have Q in the front. So this is the V, and then we can try to simplify this one with some approximation. So here it says we can approximate the two lines to P as being parallel, and the length difference as being the leg of the right triangle with the hypotenuse D. So actually, if P is not far away enough, this is just like a triangle. It's just like a triangle. But here we also assume that R is much larger than D. R is much larger than D, which means we also have this far field condition. So in this case, suppose this P is very, very far away, we will assume these two lines are parallel to each other. So the assumption is P is infinitely far away. So in this case, if we consider this angle is theta, and this is right angle triangle, because these two lines are in parallel. So we draw a line perpendicular to this line. So this right angle triangle, and then we can just consider R minus minus R plus is actually this segment. Sorry. This segment, yeah, this segment. Because if you consider P is infinitely far away, it is somehow like P is at here, and also P is also at here, somehow like this. So this is how we calculate P plus, R plus and R minus. And when we have R minus subtracted by R plus, it is actually this part. So we have R minus R plus is D cosine theta. D cosine theta is this sine divided by this sine. So we have a D cosine theta is actually this R minus R plus. And we can also approximate R plus times R minus to be R squared, somehow like this. This is R, this is R. So if P is infinitely far away, this one time this one is actually this one. Because it is like R squared minus the half of this side square, but it is much smaller than R, so we can just ignore this term. So we have the approximation like this. We have the approximation like this. And if you still remember the dipole moment is P equals QD. So it simplifies to this K times P cosine of theta over R squared. Okay. So actually, when I learned this in bachelor study, I haven't used this formula before until last year. I write a paper about the antenna. Then I actually need to use this to model the antenna, model the MIMO system, something like that. So it's very interesting. So it's like you can imagine an antenna. An antenna is somehow like this dipole, and then the propagation pattern generated by the antenna is somehow like a dipole for some specific structure of the antenna. So yeah, so even you learn physics, it might be useful. Okay, so so next part is calculating the potential due to the continuous charge distribution. So which is something like what we have done before, when we like to calculate the electric field generated by continuous charge distribution. Then we try to separate into many small parts, and then we add them together with the integration. So which is nothing but this. So the total V is equal to integration of dV over the charge distribution. And actually this dV is this K times dQ over R. So maybe this dQ is I mean this R is a function. Yeah, or the dQ should be a function of R. Just like maybe we have for example, if we have a sphere with a uniform distribution, then every charge packet will be related to the R, somehow like that. So maybe we will have a dq equals to something times dr or something like that. When you change the variable, you have something like that, then you can do the integration. So we now examine two continuous charge distribution, a line and a disk. Somewhat like before. Okay, so the first one is the line of charge. So suppose here we have a rod with a uniform charge distribution. The length of the rod is L, shown in figure B. Okay, so we can just separate this rod into many small segments like this. And for this part, this is dx along the x-axis. So this is the x-axis, and we try to take, this is the dx, and then what we concern is the electric potential at point P. Point P is at this point, and you draw a perpendicular line, and the distance between this point P and this rod is small d. Okay. So yeah, so here we have a dq equals lambda dx, similar to what we have done before. Lambda is the charge density, the line charge density, and then multiplied by the length of this segment. And yeah, and so of course we will use this one dV equals K times dQ over R. and then we can subtract this one, track this term into here. So we have lambda dx in the numerator, and actually yeah, here we have dx, so we should use x and some constant variable to represent r rather than using r here. Otherwise, we cannot do the integration. So let's consider. So this, yeah. So here, this is x. So we assume this is the 0 for the x-axis, and this is L. This is L. So this is x. This is x, and this is d. So the distance between this packet to the p is actually r equals to d squared plus r x squared. Take the square root according to the Pythagorean theorem. So we have a square root of x squared plus d squared like this. So we can do this integration, although this integration is not so easy as before. But actually we can do this integration, or actually in the appendix of the textbook we have this integration. This integration is something like this, the lateral log of this whole term. So I suppose you should have learned it in a calculus class, but yeah, actually I can just go through it quickly. So for this one, suppose we have actually we have the square root at the denominator. So actually we can write it as a -1/2 power. And actually suppose we have this is the variable. This is another constant with a plus sign here. We can just assume that x is d tangent of theta. D tangent of theta. So we'll have a dx equals to d. This d is different from this d. D secant square theta d theta, something like this, and then we can just plug it in. And also, if we have x squared plus d squared will be 1 plus tangent square, will also be secant square, d square secant square of theta, like this. So we can plug this and also this one into here. So we will have a integration of x squared plus d squared, and then take the -1/2 square dx from 0 to L to be like this. So this one is d squared secant theta. So we have a d secant theta because we have a -1/2 power. And then for dx is this one. So we have d secant square theta d theta. So actually we need to determine the lower bound and the upper bound after the change of variable. So when here we have x equals to 0, and then we plug it to here, x equals 0. X equals 0, tangent theta will be 0 because d is a non-zero constant. So tangent theta is 0 and theta should be 0 here. And for the upper bound, we should have x to be capital L, So in this case, we should have theta L to be arctangent of capital L over small d. Okay, maybe we can first write theta L here for simplicity. Otherwise, we can just put this term here. Okay, actually we can do some cancellation. We have a d cancel with d, square cancel with this one. So we have we have integration from 0 to theta L, and then secant theta, secant theta. Oops. Secant theta, d theta. So we can have a simple trick. We multiply here by secant theta plus tangent theta, and then we need to divide the same term, so that we just multiply it by 1. Okay, so the next one is, actually we can just put this one here. So for d theta, secant theta, which is actually tangent d tangent theta. So this is like d tangent theta, and then secant theta, tangent theta, d theta will be secant theta. So we have a tangent theta plus secant theta from 0 to theta L. So here we could have a lateral log of absolute value of a tangent theta plus secant theta, and then we evaluate from 0 to theta L. So which is like a lateral log of tangent theta L plus secant theta L over, if we plug in 0 here, tangent 0 is 0, secant 0 is 1. So we have something like this. Something like this. Okay, so now we need to find tangent theta L and secant theta L. So we can try to draw this right angle triangle out. So we have a d over L. L over d. L over d. So this is theta L. So this one is L squared plus d squared. So tangent theta L is nothing but L over d. So lateral log of L over d plus secant theta. Secant theta is 1 over cosine. 1 over cosine is d sine over d sine, which is square root of L squared plus d squared over d. So this is like a lateral log of d, and then we have L plus square root of L squared plus d squared. So which is actually this one. Okay, so actually we can find that if we have a rod here, we can find the potential at point P with a distance d to be this expression. So this is the charge density, and then K, and then lateral log of this one related to the length and also the distance. Okay, so the next one is to consider the potential due to a charge disk with a uniform distribution. So here we also separate this disk into many different rings with different radius. So for each of the ring, we have this radius to be R prime, and then we consider the dq on this ring, dq on this ring to be this one, dq is this one. So sigma is the surface charge density on this ring, the surface charge density. So this is the uniform surface charge density multiplied by the area of this ring. So also we can try to cut it out, and then try to flatten it and become a rectangle. So the height of this ring should be dr prime, because this is dr prime. So when you try to cut it out and expand it as a rectangle, this is dr prime. And the width of this rectangle should be the circumference of this ring, which is 2 pi r. So the width should be 2 pi r prime. So the total area for this one is 2 pi r prime times d r prime, which is this term. This is the surface area multiplied by the surface charge density, which is the total charge on this ring. Okay, so we can also use dV to be this term, and then we just plug in this term into here. So we have this term in the denominator. And then similarly, R is the distance of the ring to this point, So R should be C squared plus R prime square, and then take the square root. Here we should have a prime here. So yeah, so we can do this integration, but for this integration, it is much easier than the previous one. So we find the net potential P by adding. So we do the integration, V equals integration of V. And suppose we just separate this into many rings with different radius. So the radius should be from 0 to capital R, like what we have done for the electric field. So we integrate this one from 0 to capital L. Here, it cancels this 2 pi with this 4 pi partially. So we have 2 epsilon naught here, and then we have a sigma in the front. And then only the remaining one is R prime dr here. And then we have the square root of this one. Okay, so for this one, we can have dr prime square will be should be like 1/2 of this one is dr prime. Sorry, should be r prime dr. R prime dr prime, like this. If you don't familiar with this one, you can simply write it as dx squared. Dx should be like a dx. So you will have a 2x dx equals dx squared, something like this. And yeah, like this case. So we have a 1/2 of a dx squared equals x dx. So this is a 1/2 dr squared. And actually, if we just add a constant to it, it is nothing special. So it is actually the same. So it is like r prime squared plus c squared, like this. So actually, this term is the same as this term. We also have a prime here. So this one is actually the same as this one. So which is like this one to the negative 1/2 power to do the integration, which will be the half power, which because if we have just say w square root and then dw, so this is nothing but w square root and then multiplied by 2, multiplied by 2 because it is like because it should be like this one w to the negative 1/2 power dw. So it should be equal to w negative 1/2 plus 1 and then divide by this negative 1 by 1, like this. So we have a w square root and then multiply by 2, and then these 2 cancel with this 1/2. So we will have this one. We'll have this one, and then we evaluate from 0 to L. When we plug in z to be L, r prime to be L, we have this one shouldn't be L. This one should be capital R. This one should be capital R. So if we have a r prime to be capital R, we have a c squared plus r squared, take the square root for this term. And then if we have a r prime to be 0, we only have a c squared and then take the square root, which is nothing but a negative c here. So we have the expression for this like this one. at this one. This is the potential. This is the potential at the z-axis. So note that the variable in the second integral is r prime and not c. So yeah. Okay, so far any questions? Okay, so here it mentioned the relationship between the electric potential and the E field So the idea here is like if we have something, if we have a structure, we need to find the E field. So we can use something to calculate the E field directly. Just like in chapter 22, we just separate this structure into many small parts and then do the integration for different coordinates. So separate and find the EX, EY, EZ like that. Do some cancellation and then do the integration. Or using the way in chapter 23, using the Gauss law. Here, another way is that we can try to find the electric potential. We also try to separate into many small parts. But this integration is much easier than this one because we need to consider the decomposition for different coordinate axes. So this integration will be much easier. After getting the potential in the field, we can just do a simple operation, which is nothing but taking the derivative over the axis. And then we can find the E field along that axis. So taking derivative will be much easier than doing integration. And doing this integration is also easier than that integration. So the idea here is like that. So here it says, suppose that the positive test charge Q0 move through a displacement ds from one equipotential surface to the adjacent surface. So the work the electric field does on the test charge during the move is this one. So suppose we have E field pointing to this side, and then Q0 is the charge amount, and then ds. So if you still remember, this is the potential loss and actually the work done. So which is actually negative Q0 times dV, which is negative U equals to the work done by the electric field. So on the other hand, the work done by the electric field may also consider as this F dot ds. So in the mechanics, you learn this definition for the work done. F dot ds. So F dot ds, F is Q0 times E. F is Q times E. Q0 times E. So we can just put this one here, and then we have E dot ds. E dot ds is E times ds and then times the cosine theta. Theta is the angle between the E field and the ds. And in that case, Q0 and Q0 can cancel each other. And then we can just move this ds to the other side. So we have a dv ds negative sign equals E cosine of theta. So this E cosine of theta is like, this is the s-axis. This is the s-axis we consider. This is the equipotential surface. So, suppose we find the electric potential over the whole space, which means, for every point you know the electric potential, and of course according to that, you can also draw the equipotential surface. And suppose you would like to find the E field component on this axis, so which is like you project this E field here. So this is like the ES. ES is the S-axis component. So maybe this S-axis can be X-axis, Y-axis, Z-axis in the Cartesian coordinate, or R-axis in the spherical coordinate, or whatsoever. So this E times cosine of theta is the component on that axis. So this is the ES. ES is this component equals to this negative value of the derivative. Okay, so it's somehow, yeah, it looks easy. So, and actually it is something like this one. V equals negative E dot ds. So this is the definition when we start this chapter, we have this definition. And actually these two are equivalent to each other, which is somehow like the another form of the fundamental of calculus. When you learn the calculus, you know the fundamental theory of calculus. Okay, so which is somehow here, but actually we go through these parts. So the component of E in any direction is the negative rate at which the electric potential changes with distance in that direction. So which is like, if you already know the V, you can just take the derivative with respect to X, and then take the minus sign, which is the X-axis component. And so similarly for the Y-axis component, Z-axis component. So you can just do it independently, and then you can combine this 1, 2, 3 axis component to be the E field. Or in some of the textbook, it write it as this vector form. It looks so horrible with a triangle upside down, but yeah, it is not so horrible. And actually, for the Cartesian coordinate, so this gradient, this is so-called the gradient operator. So this gradient operator will act on a scalar field, and then it become a vector field. So this one in the Cartesian coordinate, it will be like partial x, and then I hat plus partial y times j hat plus partial z k hat, something like that. So this is the operator, how we define the gradient operator. So if we have a negative gradient v, which is like negative partial x, partial v partial x in the x-axis, and then plus partial v partial y, and then times j hat plus partial v partial z k hat. So this is actually this one already stands for these three formulas independently. So this is a compact way to write all these things together with only 1, 2, 3, 4, 5 symbol. So don't try to scale it. It is nothing special. It's just a notation. So we have this vector form for this E field and the potential relationship with the gradient operator. And actually, at the very beginning, we have a V equals negative integration of this line integral E dot ds from the initial point to the final point. Okay, so this is actually the fundamental theorem of calculus. So if you are interested in mathematics, you can just find this on the Wikipedia about the gradient theorem. So it says it's a generalization of the fundamental theorem of calculus. In calculus class, you may have learned something like integration of fx dx from a to b will be fb minus fa, and then here we have a df dx should be small f. So this is the fundamental theorem of calculus, because when we learn calculus at the beginning, we try to define the derivative as the limit f times x plus h minus f of x over h, and then take the limit x tends to 0. This is the definition of the derivative. And then for the integration, the definite integral will be like the Riemann sum, So it seems like at the very beginning, we don't have a connection between the integration and the derivative. And the fundamental theorem of calculus tells you that actually this integration, you can just find the antiderivative and then plug in the lower and upper bound and then subtract them. It will be the definite integral. And this is actually the general case, and one of the general case for the fundamental theorem of calculus. Okay, so this is somehow out of the scope of this course, but yeah, just let you know if you have interest about it. Maybe I can just finish this one quickly. So here it says the electric potential at any point on the central axis given by this one, just derive it. Okay, so starting with this expression, derive an expression for the E field at any point on the axis of a disk. Okay, so here we suppose we would try to find the EZ. Because due to symmetric, you can quickly know that EX should be 0, EY should be 0. EY should be 0. X should be 0 also. Oh. Yeah, because actually this one, if you take dv dx, negative dv dx should be 0, because this expression has nothing to do with the x and y. So as the negative dv dy should also be 0. So these two components should be 0. So let's try to consider negative dz with this expression, sigma over 2 epsilon naught, and then multiply by square root of the c square plus r square minus c, like this. Okay, so this is easy. So sigma over 2 epsilon naught is a constant, so we can just put it in the front. And then we have a negative sign here. So we take the derivative of this one, which is this is 1/2 power. So it becomes square root of c square plus r square, and then multiply by 1/2. And then here we also have a chain rule. So we should take the derivative of the inner term, 2z. We have 2z for the chain rule, and then minus 1. And here we can distribute this negative sign into here and here. So we would have a sigma over 2 epsilon naught, and then 1 minus these two and these two cancel. So we have a z over square root of c square plus r square, like this. So yeah, so we can quickly find the E field from this potential. And actually you would find that this potential will be simple, and then take the derivative. It's also simple. And then if you still remember, in chapter 21, we try to find this E field using the E field way. So actually these two ways will actually get the same solution. Nothing special. They will be actually the same. Okay, but actually just two ways to find the same thing. It depends if you can just find this integration, or using Gauss law to find the E field easy, then you just go this way. Otherwise, you may go by another way.